The one thing we have not talked about in all of the integration by parts, trig substitutions, we haven't really done very much with derivatives. I mean, the trig substitutions themselves sometimes involve derivatives, but it was usually because they had that square root floating around, or in the case of doing a u substitution with trig functions, because I could recover from having division by rewriting in simpler trig functions, usually ending up in multiplication. But let's look at the idea of a rational function. Division of polynomials is not pretty. And in some cases, dividing is arduous. So if I have something like this, if I wanted to integrate that, you'd probably want to hit me in the head with a baseball bat. And I would pretty much say rightly so, because that sucks. But that's division. And because the power on the top is higher than the power on the bottom, I could actually do the division. Turn this into whatever the quotient and remainder are, hopefully in the process make this easier. So I need you to cast your memory back long, long ago to your algebra class. You remember how to divide? There are several different methods. The two most common are long division, and the other one is synthetic division. If you remember synthetic division only works when you have an x plus a number and x minus a number, which we do in the denominator. Long division works all the time, and that is the reason I prefer it. But as the name says, it's long. But it's the same division that we do when we divide numbers. So if I asked you to figure out the simpler version of 173 divided by 7, what would you do? Without a calculator. That's the problem. Aha. 7 goes into 17 twice. 2 times 17 is 14. I subtract. I bring down my subtraction. I bring down whatever's left at the end. 7 into 33 goes 4 times. 28. I subtract that. I have a remainder of 5. So really, I would write 173 over 7 is 24 and 5/7. Quotient of 24, remainder of 5 over the divisor 7. I want to do the exact same thing here. The process is just longer. So I'm going to ask, how many times does the divisor, the thing on the outside, go in to the first thing? So how many times does x, well, okay, x into 5x cubed. Yeah?
That means 5x squared.
So I put that on top, and then I multiplied. 2 times 7 was 14. 5x squared here is 5x cubed plus 15x squared. I multiplied the 5x squared by this whole thing. Then I subtract all of that, just like I subtracted the 14. 5x cubed minus 5x cubed, those cancel, they're gone. 6 minus 15 in the x squared makes negative 9 x squared. Bring down the other stuff. Just like I brought down this 3, I'll bring down the next bit. I could bring down all of it, but since this is only 2 pieces of sequential powers, I only need 2 pieces with sequential powers. Now, like I did here, 7 goes into 33. I think x into minus 9x squared. What goes on top? What times x, Dom? Multiply. 9 times 3 is 27. Subtract that whole thing, and I get a positive 10x. Bring down the next piece. One last time. Why do I know it's the last time? Bingo. The power out here and the power down here are the same. That means I'm going to get a constant up here, plus 10. I've run out of powers of x. 10 times x, 10 times 3, subtract, I get a minus 10. That's my remainder. So I can rewrite r of x this way as our mixed behavior. I can say, instead of writing it as that big thing, I can say r of x is really 5x squared minus 9x plus 10 minus 10 over x plus 3. That's my remainder here. Remainder over divisor, just like I got 5/7. I don't know how to integrate this. I do know how to integrate this. If I wanted the integral of r of x, putting this down there would suck. But doing the integral of this, that's actually not difficult at all. Three of those pieces are really easy. The only one that's a little bit difficult is the last one. What do I do on the last one? Leo?
Would be at 10 times the natural log of x plus 3.
I do a u substitution. U equals x plus 3, then du is dx. And that one becomes much easier. So, 5/3 x cubed, 9/2 x squared, 10x. Because that will make this 10 over u du. 10 over u is 10 ln of u. U is x plus 3. If the denominator is simple like that, I can take what looked like a complicated fraction and turn it into something much easier that turns out to be logarithmic. I like that. Because that's an easy use, well, easy. It's a simpler process than what we were trying to look at before, and it's just a use substitution. Questions? The reason this worked out so well is because I could do the division. The power on the top was bigger than the power on the bottom, so I could divide. Even if the power on the top is equal to the power on the bottom, I could divide. Power on the bottom is bigger, then my fraction is basically already reduced. In this problem with my rational function, the denominator has the higher power. The division won't do anything. I've already got a remainder. The quotient is 0. But take a look at this particular denominator. That's a cubic equation. Already I'm less thrilled, because up there in the previous one, it was a simple linear factor. But there's an x in every term. Let's pull that x out. Let's factor in our denominator. This term is now quadratic. And that means I could probably, hopefully, factor it too. Can you factor that quadratic? If your first reaction is no, that's okay. You can still use the quadratic formula and get the roots, right? Give me the roots. If you can factor it, factor it. If you can't, give me the roots. And figure out how to build the factors. Hold that thought, Leo. Let people process on this one. I don't know how many of you did X diagrams for factoring back in algebra. We were the coefficient quadratic on the left, the coefficient of the linear piece, the coefficient of the linear piece on the top, the coefficient of the constant on the right, and then you're trying to mix and match to get everything to add up and multiply properly. Some of you are looking at me like I'm speaking Farsi. I'll show you. My version of factoring says, take these two outside numbers, multiply them together. What do you get? So I want to take 2 times -2, and I want those two numbers to add up to 3. Whatever I multiply to get -4. What can I multiply to get -4 that adds up +3? If I multiply these two, I get -4. How can I add two numbers to get 3? But still multiply to give me -4. So I take that middle thing and I write it -1x plus 4x. And now I factor by 2's. Look at the first two things. What's the biggest thing you can factor out of here? An x. If I pull that x out, I'm going to leave a 2x minus 1. Can you pull something out to leave 2x minus 1? If I pull out a 2, I've left 2x minus 1. So now we take the 2x minus 1's and pull those out. And we factored. Now, the reason I said you could do this from the roots, if you do the quadratic formula, you get -2 and +1/2, right? So if you get the roots and you say, hey, my root was x equals -2, then one of my factors should be x plus 2. Move it to the other side like you set it equal to 0. And if one of my roots is 1/2, then I should get x minus 1/2. If I multiply by 2 to make that match, that matches right here, doesn't it? So if you have the roots, you have the factors. If you have the factors, you have the roots. I am better at factoring than I am at building from roots, but that's not a bad way to do it. I have three simple power 1 denominators. Because all of this came from down here, which means I could think about doing this by doing this. All I've done so far is just rewrite my fraction. Doesn't look like a huge change, does it? Here's where the title of the section comes into play. I want to do what's called partial fractions. There is a way to separate fractions when the bottom is multiplied. In the integrand, the power of the top is smaller than the power of the bottom. So in each of these partial fractions, the power of the top is smaller than the power of the bottom. I claim that we can find the numbers A, B, and C so that this, when multiplied together, will be equal to this. How do I get there from here? I get there from here by making a common denominator for this side. Now I've written this a little farther to the right on my page, so I'm going to take the fraction that's our integrand and put it over here on the left. If I'd written this further to the left, I'd put it on the right. It doesn't matter. I want to set these two things equal to each other. Now, I don't know whether you're going to consider this a good thing or a bad thing. But the bottoms of those fractions are exactly the same, aren't they? If the bottoms of those fractions are the same, the tops have to be equal. So now I can figure out what A, B, and C are to make these fractions match. And there are several different ways to do that. Let's think about this for a minute. How could I figure out the values of A, B, and C? Well, over there on the right, I could multiply all that garbage out. And I could gather all my like terms. And then whatever x squared I have on the left has to be equal to the x squared on the right. Whatever x I have on the left has to be equal to the x on the right. Whatever constant I have on the left has to be equal to the constant on the right. Yes? So let's multiply all that crap out. Fortunately for me, we've done most of this multiplying. These two, when I multiply together, gives me 2x squared plus 3x minus 2. This gives me x squared plus 2x. And this gives me 2x squared minus x. let's look at all the x squared terms. From that first set of parentheses, I'm going to get 2a x squared. From the second set of parentheses, I'm going to get a plus b x squared. From the third set of parentheses, I'm going to get plus 2c x squared. All of those are x squared coefficients. How about x coefficients? What x coefficient do I get from the first set of parentheses?
3a.
Just give me that one. Now we go to the second set of parentheses, and I see I get a 2b from there. And then here I get a minus c, because that's negative right there. And then last, but by no means least, constants. Things without x's at all, there's only one. From the first set of parentheses, I get a minus 2a. Now that means I have three equations in three variables. The x squared on the left and the x squared on the right have to match each other. So this is 1x squared, and this is all of this x squared. So 1 has to be equal to 2a plus b plus 2c. X terms. The x term on the left is a 2. The x term on the right has 3a plus 2b minus c. Number terms. The number on the left is a 1. The number on the right is a minus 2a. Three equations, three variables. You know how to solve those? It's been a long time since I did simultaneous equations, man. Again, there are multiple ways to solve systems of equations. Elimination by addition, the method of substitution, using a matrix, if those of you who have taken any matrix work, seen those before. But let's make the assumption you don't remember any of that. How can I find the value of A? It's right there on the bottom. Now take that value and put it into the top two equations. Two times negative 1/2 is negative 1, plus b plus 2c. 2 is equal to 3 times negative 3 halves, plus 2b minus c. So I move the negative 1 over here to be with the 1, that makes it a 2, equals b plus 2c. Move this over here to be with the 2, that's 4 over 2 plus 3 over 2, that's 7 over 2, equals 2b minus c. You're welcome to use decimals if you'd rather. Now what? Again, several choices. I'm going to do this elimination by addition routine. Multiply one row by some number, add them so something cancels out. Because there's a minus sign here, I'm going to try and cancel out the c's. So I'm going to take this whole equation and multiply it by 2. Add those equations, the c's cancel, and I get 5b equals 9. So b is 9/5. Take that value, put it back in to one of those two equations over there on the left. Let's use the one we haven't messed with. 2 equals 9/5 plus 2c. 2 would be 10/5. So if I subtract the 9/5, I get 1/5 equals 2c. So c must be 1/10. Now, before you look at me like, man, holy shit, that's a lot of work. Yes. But almost all of the work we have done so far is not calculus. It's algebra. So it's work, not work. The goal was to do this integral, right? And we had a over x. And then b over 2x minus 1. And then c over x plus 2. Each of those three pieces results in a logarithm. I'll have to do a u substitution for the second and the third one. But let's separate these. Negative 1/2, 1 over x dx, plus 9/5, 1 over 2x minus 1 dx, plus 1 over 10, integral 1 over x plus 2 dx. First integral, ln of absolute value of x. Second integral is a u substitution. If I let u equal 2x minus 1, then du is 2 dx. Do we have a 2 next to our dx? No. So I'm going to get a 1/2, right? I'll write 1/2 du equals dx. So now this integral becomes 9/5 times 1/2, 1 over u du. The integral of 1 over u is ln of u, right? So this is now 9/10 ln absolute value of u. What was u? Third integral. Third integral is also a u substitution. U equals x plus 2, du equals 1 dx. That's nice and easy. So this becomes the integral 1/10, integral 1 over u du. So I get 1/10 ln of x plus 2. So I add up all three of my pieces, and I get minus 1/2 ln of x plus 9/10 ln 2x minus 1 plus 1/10 ln x plus 2, big plus c on the end. It worked. Wasn't thrilling. It certainly wasn't short. But notice that the hardest calculus thing we had to do was a u sub. I like that. U subs are not bad. Questions? The majority of this work is up here, doing all this simultaneous equation bullcrap, right? Solving for A and B and C. Okay. I own amazing technology that fits in the palm of my hand. There should be a way to do this here. Now, it turns out that there are actually a couple of different ways to do this based on the type of equations we came up with. So let me go back to the very original set of equations we got. This set right here. I'm going to copy this down again. So there are my equations. You know what? I think I'm going to move the numbers and the equal signs to the other side. So let's take these and just put them over here. I want you to build an array. An array? I want you to take the numbers and the signs. Notice all the A's are lined up in the first column. I don't need to keep the letter around if I keep track of the first column. So I'll just write the numbers. 2, 3, -2 in a column. I'll write the numbers for the B's in the middle column. So I have a 1 in the first row, a 2 in the second row. How many B's are down here? 0. Same thing with the third column, 2 minus 1, 0. And then the fourth column, all the way on the right, are just numbers 1, 2, 1. This is called an augmented matrix. And it's the subject of some things we do in a course called linear algebra, but I can use it right here to solve simultaneous equations. On your calculator, on the left column of buttons, the fourth button down is x to the -1. Above that, it says matrix, an augmented matrix. I'm going to put that matrix in here. So I hit second x inverse, that's where the matrix button is, and it gives me something that looks like this. These are the matrices I have. Notice that all of them right now are blank. There's nothing next to them. So I hit enter by going over to edit. Now I can edit the matrix I want. I'm just going to work with this first one. Now it needs to know how big it is. How many rows, how many columns. I always remember that rows come before columns. RC, whether you think of a beverage or you think of the fact that this is a Roman Catholic institution, I can do that. RC, rows, columns. 3 rows, 4 columns. 3, enter, 4. Hey, it built the, you see these little dots over here? Little dots tell me there's more stuff to the right. Now I'm going to put all these numbers in, going from right, so left to right across each row. 2, enter, 1, enter, 2, enter, 1, enter. 3, 2, -1, 2, -2, 0, 0, 1. When I hit that last one, it just stays there. Hit second mode, because above that it says quit. So second mode takes me back out to the home screen. Now if you hit that matrix button, it shows you there's stuff in matrix A. If you hit enter, it'll show you what's matrix A. Does that match the matrix we want? Did I type it in right? Oh, good. Now I want the calculator to do all the calculating. I want it to figure out the numbers. That's called reducing to row echelon form. Big, long, complicated name. But the initials are R, R, E, F. Go back to the matrix button. Second matrix. Middle column there says math. There's a whole lot of things this can do to matrices. Way down at the bottom, I believe it's option B, option 12, is RREF. So if I hit that, it'll ask me, okay, what matrix do you want to do this to? I want to do it to matrix A. Second matrix, matrix A. Do it to that. Hit enter. And look, -1/2. 9/5 is 1.8. And 0.1 is 1/10. I got the same numbers we wanted. So there is a method by which I can shortcut doing all that work by hand. I like that. I think that's convenient. It's very helpful as long as I have the equations. And that means that the algebra I did here, factoring and multiplying all this stuff out, that still needs to be done to get these equations. Once I have them, I don't have to do any of that. I can do that all on here. So that shortcuts one of the two big steps. The other one is doing all the factoring. I have a good way around that. As a matter of fact, historically, a large amount of calculus and algebra in general was developed because factoring is hard. And we keep trying to make factoring easier by developing new techniques. Questions? I would like you to understand, in a grand total of 40 minutes, I have done 2 problems, only one of which was an integral. The other one was just long division. These are not short. Okay. Depending on what our factoring looks like, we may or may not have to change things a little. So here, (4x over x cubed minus x squared minus x plus 1). I want to do this problem the same way. But that means I'm going to have to do that partial fraction with this. So that means I need to factor that bottom. Is there anything I can pull out? First glance, there doesn't seem to be one common factor through this whole thing. So I'll do like I did with the quadratic, and I'll look at it 2 at a time. What's the thing I can take out of the first 2 terms? Yeah? And that would leave behind an x minus 1. What could I pull out of these 2 to leave behind x minus 1, Dom? Now if I take that x minus 1 and I put it out front, I've left behind x squared minus 1. Hey, that one factors. I remember that. What's that factor to? Ooh, wait a minute. That means really I have x minus 1 squared. Okay. The problem here is I have repeated a factor. That x minus 1 is down there twice. When I go to write my partial fractions, I need to make sure it's in there twice too. So my partial fraction decomposition changes. Because it's up here twice, it's got to be down here twice. There's another option if you don't like that. You could also write because you'll notice the power on the bottom is x squared, and that means that the top has to have a smaller power, which means that has the first power. But I think actually doing it this way is easier than doing it this way. There's a little more algebra required to do it here. They both work. It depends on which algebra version you like. I will say that neither of them are trivial, because we're going to have to go through that same thing of finding my common denominator and fleshing all of this out. Now, I will say that I stole this particular example from the textbook. So if you do this the way I have up here, you should end up, have them in the right order? You should end up with C equals -1, B equals 1, no, A equals 1, and B equals -1. I believe. Because I realize that my book, my notes, I have these switched into a different order. So I'm double checking as I go across. But from here to the bottom of this problem, it's a page of algebra. Very little calculus involved in this part. Just like on the homework you gave me, there was a whole lot of trig, not a lot of calculus. And there was a bunch of u substitutions to do trig functions, but there was a whole lot of trig identities that I needed to do all that. There's a lot of algebra I need to do this one. Questions? Yes, ma'am. The bottom of this is really x squared minus 2x plus 1, right? If I multiply that out, the top has to be a smaller power. The bottom power is 2, then the top power has to be 1. As a matter of fact, that's my next claim in the next example. But Dom, you had something else on this.
If you like B, like 3 different portions could go under A, B, and C, and why wouldn't it just be x minus 1 and x minus 1?
Because if I had that extra one, that's because this is repeated up here, right? It really needs to be squared in the bottom. And so having it once and twice, well, then my common denominator is only going to have it squared. And that's really because this is easier to deal with than this. But this is really what I should be doing. It's just much harder. So doing the repetition, if it was cubed, I'd have 3 of them. I'd have a over x minus 1, b over x minus 1 squared, and c over x minus 1 cubed. I get 1 for each power. And it's got to have all the powers going all the way up. Do you also have a question, or was I hallucinating your hand? Doesn't matter at all. You can put them in any order you like. You can make any of them A, any of them B, any of them C. You just have to be consistent within your work. Here? Because I've taken account into that here. When I do my common denominator, it works out the same. That's the algebra trick involved in this silliness. Like I said, it's in there, it's in hiding. And repeating factors like that makes it, quote, simpler. It makes the algebra work out nicer to do it that way than the one on the bottom. But let's just do the partial fractions part here. I'm not even going to worry about the integral. I'm just looking at the algebra needed. What do I do factoring in the bottom there? Leo.
It would be x times x squared plus 4.
Crap. X squared plus 4 can't be broken down any further without involving complex numbers. I don't want to do I in this course. No, that hurts. That's painful. I'm not working. No. So I have to leave the quadratic in the bottom, right? If I break this up, it's going to be a over x, and then the other piece is going to be x squared plus 4 in the bottom. Nora, what has to be on the top this time has to have both an x and a number. Even though there's only one of it, right? The power on the top has to be smaller than the power on the bottom.
Even if you have two things, you still have to have A, B, and C.
In this case, because my power on the bottom there, where I started was a 3, I'm going to need 3 coefficients total. That's almost always how I can keep track of how many letters I'm going to have, is looking at the power involved down here. I'm going to need more of these. As a matter of fact, I believe it's example 6 in the textbook. If you really want pure psychosis, example 8. Example 7 here, x minus 1, x squared, x plus 1 cubed. X squared plus 1 cubed. So this needs 1, 2, 3, 4, 5, 6 different fractions. 1, 2, 3, 4, 5, 6. I get 10 variables. There's no way on God's green earth I'm doing this by hand. This gets shoved into a computer and, hey, solve this thing like I did with the matrix here. But you'll notice the x squared is cubed. So there's x squared plus 1 on the bottom, Dom, and x squared plus 1 squared on the bottom, and x squared plus 1 cubed on the bottom. And Nora, in each of those numerators, I use the same simple thing because it's a repetition. If I really want to do it all at once, then I'd have x squared cubed, that would be an x to the 6th. The top would be x to the 5th, x to the 4th, x to the 3rd. I'd be there forever solving that one. I guarantee you, I will not make you do stuff that needs any more than 3, maybe 4 once in a while. But we're going to do them all on the calculator. I don't want you to do simultaneous equations by hand. That just takes so long and is so tedious. Now, a question for you. Let me make an assumption that I finished this and I end up with B is, hang on, I actually have the numbers somewhere. B is 1. And C is -1. How do I do that integral? Answer, I break it up into 2 separate integrals. Really, This one is a U substitution. This one is an inverse trig. That's going to be an inverse tangent. Remember when we said we had x squared plus a squared? We used the tangent. This turns out to be 1/2 the inverse tangent of x over 2. Why is it 1/2 and over 2? Because that's the square root of 4. That comes from our trig substitutions. But every time you see a quadratic factor in the bottom, you're probably going to see that inverse tangent show up. Put a star on that formula, write it down, we're going to use it a bunch. Now, again, I moved fairly quickly through just a few examples. So I did a bunch more of these. They're on our Canvas page, all typed up nice and neat. There are 2 different pieces on trig substitutions and on partial fractions in our Canvas page. There's that handout that I just showed you, and then there's the how to do the simultaneous equations on your calculator. They're both there in our handouts section. All right? Thank you all very much. Have a wonderful weekend. I will see you all on Monday.